During this Tech Talk, we will discuss our current Navy Phase 2 SBIR project that builds on our portable, non-contact inspection technology for fasteners and defects on aircraft outer mold lines. Since the inception of the SBIR program, Creare has been focused on developing and commercializing pioneering innovations. Within the DoD and the Navy, we transition those innovations into products, systems, and technologies that enhance warfighter health, efficiency, effectiveness, and lethality. Over the last 20 years, SBIR has become more embedded in the technology roadmaps for multi-year defense programs that span the life cycle through concept generation, development, design, production, fielding, operation, and sustainment. Creare transitions of SBIR technology have resulted in 3 spin-off companies, 14 licensing agreements, and numerous custom products. The combined direct and third-party revenue from spin-offs, licenses, and direct product sales exceeds $5 billion. Our commitment to technology transition and technical diversity enables Creare to succeed in critical areas related to healthcare, aerospace, as well as military applications on land and at sea. As the Navy described in a recent Transitions newsletter, Creare is the quintessential SBIR success story. For background, the Fastener Measurement Tool, or FMT, is a currently fielded device used for rapid, highly accurate inspections of unfilled and filled fasteners on the F-35 production line at Lockheed Martin in Fort Worth, Texas. Fundamentally, our FMT replaces several time-consuming, inaccurate, and subjective methods to measure fasteners to ensure low observability compliance. Since its introduction to F-35 production in 2018, the FMT has demonstrated substantial benefits, including reduced touch labor, a reduction in the number of inspection tools, and escape prevention. Most critically, the FMT has been a key enabling technology for F-35 production to achieve full rate, which is required to meet agreed upon cost targets. Currently, over 100 FMTs are supporting production in Fort Worth. The current technology transfer program focuses on further software and hardware enhancements to the FMT to broaden its reach for F-35 sustainment and other programs. First, the FMT program expressed a strong desire to extend the capabilities of the FMT into countersink measurements. While measuring unfilled fasteners can catch non-compliant assemblies, the ability to measure countersinks and virtually install a fastener can catch these issues further upstream in production, enabling possible corrections before parts have been assembled. Second, there was a desire to revise the FMT hardware to remove the belt pack and create one unified tool platform while addressing the desire to use the tool in the EU and UK markets for F-35 and other programs. Third, we determined that there was a strong need for an FMT-like solution for damage assessment or sustainment on the F-35 aircraft during operations. Currently, such damage is cataloged by operators using Mylar sheets to transfer the damage geometry from the aircraft to the flat, traceable screen of a computer. Not only is this process highly inaccurate, it is extremely time-consuming. Having a repeatable and automated point-and-shoot flight line option for post-flight damage assessment and integration into larger-scale performance models will reduce operational maintenance burdens and get the aircraft flying sooner. Countersink measurements have been completely developed under this SBIR program for the existing FMTs in use and all future units. This capability enables the requirements for unfilled fasteners to be applied before a fastener is installed, which facilitates corrections further upstream in the manufacturing process. While many fasteners on the aircraft are as simple as the one in the upper left, there are a large number of special cases that we worked with Lockheed to successfully address before full implementation of countersink measurement. We have also focused on upgrading the FMT hardware in this program. First, we eliminated the belt pack to create one unified tool that will be easier to use and more robust. Second, we developed design approaches to address various regulatory requirements in the EU and UK, as well as specialized requirements related to operating near fueled aircraft. Third, based on the upgraded FMT design, we developed a prototypical tool platform for defect measurement, which combines the measurement of the actual defect with a wider angle measurement to assist in locating the defect on the aircraft automatically. With respect to the defect measurement tool, or DMT, the present slide describes the overall process in more detail. The idea is to reduce the inspection time for a particular defect from many minutes to seconds, while dramatically improving the geometric representation of that defect. Because of the limitations of the current inspection process, engineers and operational staff spend many hours, and sometimes days, trying to exchange detailed information about particular defects on critical areas of the aircraft. Our tool not only creates a high-fidelity, accurate digital representation of the defect, the scan of the surrounding area, coupled with a novel software algorithm, enables the accurate location of that defect on the aircraft OML, as shown in more detail on the next slide. The direct scan of the damaged region using the DMT is translated to a map that can be used to directly display critical information, such as the characteristic length and width of the defect, its maximum height, volume, and area. Importantly, the DMT also provides a detailed measurement of the depth of that defect. As mentioned earlier, the separate large area measurement inherent in the DMT is statistically matched to a model of the F-35 airframe to automatically locate the damage on the outer mold line. We have conducted numerous tests at a local Air National Guard base in Vermont that is flying F-35s. These tests have provided critical data and demonstrated the numerous advantages of our DMT relative to the current process. These include the automation of defect measurement, localization, tracking, as well as reduced labor, decreased aircraft downtime, and overall improvements to aircraft performance assessments. The current program will result in DMT prototype hardware and software, and future development will aim to productionize this system with a focus on integrating with current aircraft performance tracking tools such as LODEM and LOHAS. Creare and our affiliate IDARE have become key suppliers of high-performance metrology tools for aerospace applications. These span the two versions of the FMT, the DMT, and a robotically mounted version of the system currently being developed to inspect C-130 aircraft wings at Robins Air Force Base. The Creare IDARE team is a model for successful innovation, technology development, and transition through the SBIR program. Additionally, IDARE is working with respected aerospace distributor Accurex to increase the market for FMT-related products to the commercial aerospace market. Thank you for your time and attention, and please don't hesitate to reach out with any questions.